Bonjour tout le monde. Alors, bienvenue à cette deuxième édition des séminaires d'astronomie et d'astrophysique du CREC à l'UDM. Aujourd'hui, on a le privilège d'avoir la docteure Eve Chéry, qui vient de l'Université McGill, donc pour parler de caractérisation d'exoplanètes, d'atmosphère, de formation. Le docteur Lee a fait tout d'abord un postdoctorat. En fait, a fait son doctorat à l'Université de Berkeley, a fait un postdoctorat première année là-bas. Ensuite, il y a eu un autre postdoc à l'Université de Caltech et est maintenant professeur, donc, 2019 à l'Université McGill. Alors, bonsoir, Lee. Je laisse la parole.
Thank you for the introduction. And pardon me if I'm not speaking in French. I can understand you, but I do not feel comfortable enough to speak it. So I will continue in English. So I'm very glad that I was invited. As you might imagine, there's something going on over there at my affiliation. So I will be moving back to California at the end of the calendar year to take up the associate professor position. So I'm super excited about the opportunity, but it does mean that this might be one of the last times that I will be close academic neighbors with you all. So very glad that I have this chance to discuss my science before my departure. So I'm a theoretical astrophysicist, and I mostly study the formation of planets, particularly the exoplanets, but I'm at UDM where there's a huge group working on atmospheres, characterizations, deep characterizations of planets. So I will frame this discussion where I'd like to make the connection between the atmospheres, the formation, as well as the orbital architectures of planetary systems. So if you take a look at the confirmed exoplanet, this comes from the NASA Exoplanet Archive. When we measure the planet properties, there are three fundamental properties that we mostly start with. Those are the masses, orbital periods, and the size of the planet. So here we're looking at mass versus orbital period. The color coding is with respect to the different detection methods. And by far, it's a bit hard to see here, but by far it is the transit methods that gave us the most number of planets, which means that our exoplanetary census is very much focused towards short orbital periods, very close to their own host star. And this is also where we have the best chance of doing some deep characterization of these planets. So if we zoom in and take a look at the size and mass together, then we can at least get some bulk sense of what the planets are made out of. So the dashed lines here, those are not physical. That's just to guide your eyes. That corresponds to constant density, with the upper one corresponding to the Jupiter, the lower one corresponding to the Earth. And as the astronomers and especially exoplanet people probably appreciate well, this is very different from saying that what is the mass radius relation for a given composition. Obviously, that will depend on the physics that governs the interior structure and the equation of states. So they will look very different. This is just to guide your eyes. So by looking at this, we can get an idea of the planets that are massive and large corresponds to something that has really thick gaseous envelope. So hydrogen, helium dominated gaseous envelope. And for those that are light and small corresponds to something that is almost a bare rocky object. The question is about these points over here, which we call the mini Neptunes or sub-Neptunes. They're sort of in between, and there's a very well-known degeneracy as to whether they should be considered as some rock with a thin hydrogen helium dominated envelope on top, or a much thicker, like water dominated envelope on top. They can give you the exact same result for mass and radius, so we don't actually know just using these fundamental parameters. So one of the ways in which the community is trying to probe is to look at the chemical composition within the atmospheres of some of these targetable planets, to see whether we can get some sense of like what is the water mass fraction, what are some other chemical composition that we can probe, so that we can have better understanding of what exactly these planets are made out of. Keep in mind that we're very often limited to the upper altitudes of the envelope, so rather than deeper down. So with that in mind, as I mentioned, my sort of approach to exoplanet science mostly comes from formation. So I'd like to pose 3 questions to frame this discussion. The first is that when we think about how planets form in the protoplanetary disk, which are the leftovers of star formation, what we often call spinning disk of gas and dust around the young stars. And depending on how far you are from the star, the compositions of both gas and dust can change because of the different temperature. So that means we might expect to see different sort of initial composition of the planets depending on where those planets form. So how exactly do disk properties bear on exoplanetary composition, radius, and mass? And once you get those initial conditions, then how exactly can we connect that to what we currently observe, which are present-day properties like present-day atmospheric composition? Because there are many things that can happen between the initial formation and wait like a few gigayears or so, and then see what happens as we observe right now. And finally, often we look at individual planets, but those individual planets come in a system of multi-planets. Just like our own solar system, exoplanetary systems also come in multiple planets. So can we make any connection? Are there any sort of trends that we can find between the planet composition as well as the architecture of the host systems? So let's start with the formation part. And for those of you in FX and have heard my talk, you probably have seen this cartoon and hear me talk about this so many times. But it's such a fundamental physics that underpins the growth of a planet that it's really worth repeating. So let's start with the picture of you have some massive rock that will create a planet, and it is embedded in the protoplanetary disks, this gaseous nebula. As long as the rock is massive enough, you can define its gravitational sphere of influence. In most cases where you're looking at short period planets and planets that are more massive than about a few Earth masses, then it's almost always the Hill radius. So the gas inside that sphere will be bound to the gravity of the rock against the tidal acceleration from the star. That binding process, though, it's a release of gravitational energy, which means it's going to heat up the gas. So you will see a temperature gradient after the binding process. And as you all know from our physics classes, nature really does not like having gradients, including temperature gradients. So it will try to erase away that gradient by cooling off the gas. And a gaseous layer that is cooling off is going to shrink. So that means this planet will have some room, some empty room to refill its Hill sphere and build thicker and heavier gaseous envelope. So this is the very basic picture of how planets build this gaseous envelope. Now, the rate at which that happens, that depends on the thermal structure. And for the thermal structure, the modern understanding right now is that there are 3 layers. Used to be 2, now it's 3. We start with the outer advective zone. This corresponds to the region, the uppermost layer where the disk inflow, the inflow of the disk gas comes in and cycles out around the local orbital time. And then we have the bound sandwiched radiative layer, and then the innermost convective zone. So there has been a bit of a debate of like what exactly the role of the advective layer is, because the accretion process is given by the thermal process. So how exactly, what exactly is the role that advective layer plays in the thermal evolution of the envelope? And at least what we're finding right now is that it's not that important. In fact, where it's really important is actually the deeper zone. And that's because most of the mass, around 80 to 90% of all the mass, is all locked into this convective zone, and the gas is all centrally concentrated towards the core envelope interface. So why is that? And that all happens because of the specific physics of hydrogen molecule dissociation. What does that do? So this inner convective zone usually occurs below about 2500 Kelvin. that's where it can start dissociating hydrogen molecules. So when you have free hydrogen atoms, it can start combining with the free electrons that got off the metallic species, the outermost valence shell. So you have H- ions, but those H- ions can very easily lose that extra electron. So that bound-free transition gives us the dominant source of opacity, and it's a very strong function of temperature. So the deeper you go in, the envelope just gets so opaque that it's really hard to transport energy by radiative diffusion. So that's why convection prevails. And furthermore, when you have dissociation of hydrogen molecules, that needs energy. So that energy, instead of going to the kinetic degrees of freedom, so kinetic motion of the particles, it goes into dissociating hydrogen molecules, which means that when we take a look at the local temperature gradient, it basically thermostats. In other words, if you're familiar with the stellar structures, the adiabatic index goes to something close to 1. So it approaches something like an isothermal, even though it is an adiabatic profile. And that means the mass profile is centrally concentrated rather than outwardly concentrated. So the net effect of all of that is when we take a look at the sort of time evolution of the growth of the envelope mass, it is by far most sensitive to the mass of the core because of that central concentration. It of course also depends on for how long you can accrete and also the metallicity, so the general composition of the envelope that you accrete. But by far, it is really the core mass that is the most important, even when you account for that advective layer. So more overall, when we compute the expected envelope mass fraction as a function of core mass, the different accretion time and to a degree, the different metallicity will give us some scatter, but the upper envelope, sort of the maximum you can have, will change a lot depending on the mass of the core. And here, this straight line over here in log space, that corresponds to the thermodynamics of physics that we have over here. And you'll notice that there are parts where it seems to sort of break away from that relation that we've been discussing. So at the lower limit, this is the place where you reach the maximally cold state where the envelope just, it erases completely the temperature gradient. So there's no more room to cool and therefore no more room to accrete. This actually has an implication for the famous radius gap for those of you who work in exoplanets. I'm not going to talk about that here, but happy to discuss during Q&A and offline. On the high mass end, this corresponds to the change in physics that governs the final mass of these planets. So what happens here is that when the envelope mass becomes comparable to the core mass, then you have such a thick and heavy envelope that the cooling time scale just gets really, really short, like catastrophically short. And therefore, this triggers what is called the runaway gas accretion, and you have the formation of gas giants like our own Jupiter. The important thing that I want to point out here, though, is that this means that across certain critical core mass, there is a switch in physics that governs the growth in mass. And this will show up in sort of like demographic metric, like the overall mass function of a planet. Now, another important thing to note here is that this critical core mass is not a fixed number. It will depend on what the planet is made out of and how far they have formed with respect to the central star. So what you're seeing here is the variation of the critical core mass as a function of the orbital distance and as a function of whether there are dust grains in the upper envelope or not. So you can already see that there's quite a bit of a difference. And the reason for that is because under dust-free condition, the envelope becomes a lot more transparent. And that is because when it's no longer dust grains that dominate the opacity, it's the gaseous molecules. And when you go farther out from the star, the disk gets colder, and you have the gradual freezing out of the internal degrees of freedom. So there's there's like a less lines to excite. So the envelope becomes more transparent, easier to cool, so you have faster accretion and faster growth, which means that critical core mass that caused the switch between thermal and hydrodynamics, it goes to lower and lower core masses. Yeah.
What's the dust-free environment? How can we get an environment that is dust-free?
Yeah. So it's a bit of a misnomer because this doesn't literally mean that there's no dust whatsoever. It means that the dust grains do not contribute to the opacity as much, which happens when dust grains coagulate and gets larger. And then it'll be followed up by like raining out within the envelope.
So I understand the dust-free is more about the size of it.
Exactly, it's the size distribution that's different. Yeah. Right. Okay, so this critical core mass will show up as a break in the mass function, and this mass function is what we will find with the Roman Space Telescope through their microlensing survey. The science case that I want to point out here is that the microlensing community is usually considered like a black sheep of the family in the exoplanet science, and I find that really, really sad. But I think there's a real science case here where we can make a connection between what we're currently doing with JWST and what we will find within maybe the next 2 years or so with Roman. So the argument is that because this break in mass will change depending on what the planet is made out of, and furthermore, we have the best chance of differentiating between the different composition at a few AU, where microlensing is the most sensitive. If we can nail down where that break occurs, we can compare that to the compositional studies that we're currently doing with JWST and make that comparison between what we see at this short period orbit planets versus the initial compositions that we expect to find with the location of the mass break at a few AU, where we still expect to have the memory of the initial conditions. And here, we're just doing a simple calculation of dusty versus dust-free. As we've discussed, it really just corresponds to different size distribution, but we can repeat this analysis by playing around with the different chemical composition as well. Okay, so we've been talking about the formation and therefore initial gas mass fraction, but as I have alluded to at the beginning, we need to make that connection. We need to somehow make that bridge to the present day observable, like mass and radius, and also chemical composition. And there are different processes to consider when we try to make that bridge. So the first is the simplest one. It's a simple thermal contraction. When the envelope is just bare, so all the disk is gone, then you will have a temperature gradient right across the interface. So the planet will start to shrink. Some caveat here: if the planet is close enough to the star and the irradiation is high enough, then that can also cause some puffing of the planet. And that irradiation will also cause things like the mass loss. So the most important mass loss process right now is what's called photoevaporation. So X-rays and UV photons from the central star will ionize some of the upper layer, and that thermalizes with the surrounding gas and drives off the wind. And this is particularly relevant for short periods inside 30 to 50 days or so. It has the capability of transforming mini Neptune into almost a bare rocky object. And finally, there are also things like pollution. So you form a planet, it has a certain composition endowed from the disk, but there could be some leftover solids around, and that could rain down onto the planet and change the final composition. So we'll start with the first two, and then we'll move on to pollution. One of the ways in which we can probe these post-formation evolution is to take a look at young, puffy planets. So by puffy, I'm talking about planets that are larger than around 6 Earth radii. In the community, those are considered as something that can be categorized as gas giants or Jupiters. And by young, I'm talking about something that's younger than a gigayear. Most of the exoplanets that we see right now are more like a few gigayears, but there are a small subset of planets where they're actually quite young. So as young as like 10 million years or so. And the reason why this sample is interesting is because even though the planet that we observe right at that age are large enough to be called as Jupiters, they could very well be just puffed up mini Neptunes because they're still undergoing that thermal contraction. So in the NASA Exoplanet Archive, you find about 24 such planets. And what we do is using the size, the age, and the flux, we try to put some constraint on the plausible masses of such young planets. So here's one example of a TOI 1227b. And what you're seeing are the different solutions, different structure solutions for different total mass and the different metal mass within that planet. And we're assuming the gas is almost purely hydrogen helium with solar metallicity. And we're comparing the radius, the observed radius shown in horizontal line with the 1 sigma error bar. Again, there's a huge degeneracy in the structure models. You can see that this particular object can be either brown dwarf, a Jupiter, or puffed up mini Neptune. So we need to do a bit more to narrow down this range a bit more. First of all, we can immediately rule out the brown dwarf solution because that is way too dense for a brown dwarf at that age. Just from formations, what we've been discussing thus far, we can rule out the very low density end of these solutions because it's really hard to create those puffy planets. There are some exceptions that I'll show in a bit. And then we can further constrain the lower limit on the planet mass because these planets would be way too light and they will be destroyed by photoevaporation over their system age. And we can also rule out some of this Jupiter solution because if they were truly Jupiters, then they are way too metal heavy for their given stellar metallicity. This comes from the empirical mass metallicity relationship with the caveat that this is really empirical and there are some outliers. So this kind of constraint that we make is really a statistical constraint. So anyways, the upshot is as follows. So these are all 24 such young puffy planets, and these are the limits on the masses that we can make as a function of age. One thing that pops out immediately is that for the planets that we can call as a true gas giants tend to be older. They are older than 100 million years. And that actually has a really interesting implication of like how exactly hot Jupiters form. It points towards a late stage dynamical scattering in, but that's a bit of an aside. That's not the point of this discussion. What I would like to point out here are this very low density objects, the planets with the mass measurements, starting with the HIP 67522b. This one has an upper limit on the mass based on transmission spectroscopy. And given its properties, we expect this planet to be currently undergoing a massive mass loss, and we should be able to detect that. And I'm told that there are groups who are looking at it right now. And then there are these planets where their measured masses fall way below the theoretical constraints. So these classify as super puffs or cotton candy planets whenever I talk to the press, because they have the same bulk densities as cotton candies, the ones that you can find in grocery stores, not the ones at carnivals. So let's take a look at these planets a bit more carefully because they cannot be explained by sort of like fiducial and traditional ways of formation. So how exactly can we form the super puffs? And for this, we go back to that argument of opacity. So the plot that you see on the left, that actually comes from Caroline's paper. I was told that she's now a doctorate PhD. Yeah. So congratulations. That's really exciting. And this is a WASP-107b. It's one of the crazy super puffs. And to explain their super duper puffiness, what you have to do is you do have to go to far out distances, and again, dust-free accretion, so that you can accelerate the gas accretion process thanks to the lower opacity. Notice how you really do have to go beyond the 1 AU to explain this particular object. So same thing happens for other super puffs in the catalog as well. Now, a lot of these super puffs are found in multi-planetary systems, and they're also much closer to the star than 1 AU, which means once they form, they have to migrate in by those planets interacting with the disk gas. And if you have multiple planets that are undergoing slow enough migration, then we expect them to sort of lock into mean motion resonance, which means that their orbital period ratios are integer ratios. In fact, many of the super puff systems, I think all of it actually, are known to be either formally in resonance or near resonance. So it seems like the data are sort of like all together is consistent with this picture of formation far out and followed by migration. Another data that we can look for based on this is that if planets are forming outside 1 AU, that's close to the so-called ice line. This is the location beyond which the disk is cooled enough that the solids are expected to be coated with water ices, or the solid, sort of the solid phase of the volatile species. So as these planets are forming, if it gets polluted by those icy grains, and if you maintain those in the upper envelope, then we might also expect to find water features or low C/O ratio. Now, based on all those different sort of formation consideration, we'll try to nail down with more certainty where exactly those super puff systems that I've mentioned have formed. And those are our V1298 tau and Kepler-51. All right, so here's the outline of the calculation over the grid of the initial gas mass fraction and the metal mass. Let's pick out a grid point. And then we go forward in time undergoing photoevaporation of a given planet at its present location. And then we calculate the final expected gas mass fraction, and then calculate the expected radius of that planet compared to the measured radius and mass of the planet. If they agree within 1 sigma, then we deduce the formation location such that this given metal mass is able to obtain this initial gas mass fraction. And notice how there is now a dependence on the disk temperature, which gives us the location. And then we do this for all the other systems with all the other planets within a given system, and we find the resonant solutions between the adjacent planets. So here's the result, starting with V1298 tau. Planet D is the closest one. This one's interesting because it turns out this planet is most likely explained by in situ formation, so close to where we currently find them. And it's at around 10 days or so. It's very close. And that's interesting because that's actually near the expected edge of the disk. It's sort of like an inner boundary of planet formation. If you're wondering about sort of the morphology of like what exactly you're seeing here, sorry, the texts are really small. So what you're seeing here is that the solutions that are consistent with this current measured radius and mass is that you need slightly lower initial gas mass fraction for lower metal mass, and that's because this is a really young system. There's a high level of irradiation, and that puffs up the low mass planets. So in order to explain a given radius, you need slightly lower gas mass fraction. That's all that's going on. Now, for planet B and E, which are farther out, they do require formation beyond 1 AU. So the picture here is that the innermost planets are formed near the disk edge and got parts there, and the outer two planets have undergone migration and entered something close to the mean motion resonance. And we can find the 3 sets of solutions that are in resonance. Now, what about Kepler-51? This is a very well-known super Puff system. Doing the same analysis, we basically find that both planets have to have formed beyond 1 AU and then underwent migration. You see a slightly different morphology of the solution sets. Here, Kepler-51 is much more evolved. It's around 500 million years, so they're more susceptible to mass loss, which means that you need higher initial gas mass fraction for a low metal mass, so that you can explain its present-day envelope mass fraction. Now, one interesting thing is that based on some ongoing results led by Peter Gao and Carnegie, the C/O ratio of planet B is extremely low. And that's interesting because perhaps that might suggest that this planet has accreted a lot of water, leading to low C/O ratio. So let's test that. And we're going to test that by looking at what exactly is the compositional gradient within the atmosphere after the post-formation pollution by grains. So the picture, here's the picture. We have the disk, it's gas and dust. We have a planet that is undergoing migration. So as the planet migrates in, it's sweeping up the solid material in its trajectory. Now, there is some special location, as I mentioned, within the disk. It's around 1 AU for water. So outside of 1 AU, we're going to assume that all the grains are pure ice for simplicity. Inside, we're going to assume that's pure silicate. And then here's how we're going to compute pollution. So that's an envelope. Pick out a solid that's falling through, and it's falling through the envelope due to gravity acted against by the aerodynamic drag. And on its descent, it's going to be heated up just like the meteors in the Earth atmosphere. And there's going to be a thermal ablation, so sublimation of the material that's polluting each of the layers as it falls through. And that depends on the temperature of that grain. And there are three components that give rise to the temperature. The first is the radiative heating and cooling as it interacts with the surrounding gas. The second is frictional heating as it falls through. And the third is evaporative cooling as it releases the latent heat. Another thing to note, this infall is not some very gradual, mild infall. It is very energetic. It's supersonic infall. So we also have to take into account that the gas sort of downstream of the motion will undergo adiabatic shock. And on top of that, if you want to calculate C/O ratio with more accuracy, we also take into account the pollution by refractory carbon species. Apparently, in the astrochemistry literature, they use kerogen as a proxy, which is oil shale. We actually had to dig through the literature in the material science and those by oil companies to figure out the thermal properties of oil shale. Apparently, it's very complicated. Okay, so here's the result of the C/O ratio as a function of the gas pressure. So we're going from upper altitude to lower and lower altitude, deeper into the atmosphere. On the left, this corresponds to rapid migration. So you'll notice how the C/O ratio is quite high. And that's because, and that will happen when the planet is really zooming in. So, it's the migration is so rapid that it barely spends any time beyond the ice line. So there's barely any water accretion. On the right, there's a marginal migration, so more gradual, slower migration, and that allows for the planet to spend more time beyond the ice line, so there's a lot more water accretion, and there's a steep rise in C/O in the deeper region. That happens because now the kerogen starts to get ablated as well. If you're interested in what does this correspond to in terms of the water mass fraction profile, it can be really high. These are all local mass fraction. It can go up to 1. Actually, if you take a look, if you zoom in, it's actually beyond 1 in some cases. So the upshot is that the post-formation pollution of this grains beyond the ice line, it can be pretty extreme. You can come up with a pretty extremely water-enriched envelopes, which means that even if you started with like hydrogen helium dominated like mini Neptune, by pollution, that can transform that planet into something that is more akin to a water world, depending on your definition of water world. Okay, so we're now like starting to sort of connect the atmospheric composition and the architecture of a system when you have multiple planets in a given system. So I'd like to delve into that a bit more and now try to talk about what exactly is the effect of having that outer planets on the measurable quantities of the inner planets. So this is relevant because we've seen this cartoon a lot throughout this discussion. It looks like everything's nice and static. It isn't in real life. All these grains also undergo inward drift because they're being dragged by the gas and losing angular momentum. Now, introduce a planet. A planet is going to perturb the disk and drive up a wave through tidal interaction. And that wave can create some local pressure perturbation and the local pressure maxima. So you might have heard things like the dust traps. If you go to talks that talk about this and the disk-planet interaction, what's going on here is that on the outer side of this pressure bump, the gas pressure bump, the gas is moving at a sub-Keplerian velocity because the pressure gradient, the negative dp over dr force, is acting against the stellar gravity. So the gas is moving more slowly than the grains, and it's dragging on the grains. Grains are losing angular momentum, and it's moving in. But on the opposite side, now the pressure gradient force is acting in the direction of the gravity, so the gas is moving quickly at a super Keplerian velocity. So now the dust is gaining angular momentum and it's moving outward. So that's why we think this pressure trap or pressure bump causes the trapping of the dust. So this simple picture allowed people to deduce that, well, maybe having a massive outer planet will cause sort of the stopping of the delivery of the volatile species in the inner planets, in the inner region. And sometimes people go to extreme and say that, well, maybe you completely stop the inward motion of the inward drift of the planet building blocks. So we shouldn't see the inner planets when we have the outer giants. So let me address that a bit and say that actually having the outer giant doesn't mean that you're going to block out entirely the influx of the planet building blocks, because in the observations, we see that compared to the rate at which we see the giants around stars in sort of a unbiased survey, it's actually lower when we pick out the systems that already have the super Earths. In other words, there's a positive, very strong positive correlation, whereby if there are inner small planets, you tend to find that those systems will also have the outer gas giants and vice versa. One thing to note here is that this trend or this correlation has been debated quite a bit in the literature. And it turns out if your sample happens to be biased towards a low metallicity star, you can completely get rid of this signature. So this architectural state of the inner small planets and outer large planet happen to be more determined by the total mass content, sort of like how heavy your disk started with. So in other words, if your disk is massive enough so that you are able to create the outer planet, you will have no problem also creating the inner planets, because not only do you have enough mass, but also the disks, these protoplanetary disks, are pretty inefficient at forming planets. If you actually just calculate what is the efficiency at which these disks transform its mass content into planets, it's about 10% or less, which means as the planets are forming on the outside, a lot of the solid material are drifting right in. So you will have no problem creating the inner planets. Okay, But what about that second more nuanced question of, okay, so maybe you can form the inner planets, but like what about the delivery of the volatile species? Like would that be stopped by having this outer planet? And for that, I like to boil down the question into how efficient are these dust traps for different kinds of planets? In 1D calculation, as I've mentioned, it is expected to be a perfect trap because the dust gas relative velocity formally goes to 0. In 2D hydro simulations, we still find that it is a nearly perfect trap. And then we ran 3D simulations, and as you can might imagine, that things are a lot more complicated. So what you're seeing here is the dust flux in color. And you can see this different spiral patterns because there's a planet right over here that's perturbing both the gas and the dust. And if I can play this. Okay, that's supposed to be a movie. I'm not sure if I can play it. It doesn't really matter. That one, what you're seeing is a vertical distribution of the dust flux. And if I were able to play it, we're going sort of in azimuthal direction. So we're going through the different azimuthal slices, and you'll notice that it's a very complicated pattern where there are some regions where the dust completely goes in and some regions where the dust moves outwards. And it has both radial and vertical distribution and azimuthal distribution. So if you just look at quantitatively how much of the dust influx gets stopped, you'll notice that it is actually a pretty small fraction. So thinking of the outer planet acting as sort of a barrier for the delivery of any of the outer species may not be so simple as we have previously thought. Okay, so to summarize, we started our discussion with how we can connect sort of the disk properties, where the planets form, the initial conditions, and how we can make connection to the observable properties. There's something special within the disk where planets form beyond the ice line at large orbital distances because of two reasons. First is the disk is colder. So in general, you expect to find lower opacity. That allows for the accelerated gas accretion so that when we take a look at the overall mass function of a planet, we expect to see some sort of a break in the mass function that depends on the composition of the planet, depending on what the planet is made out of. And furthermore, the best location to take a look at this is at UAU. And that I think is a strong science case to make for Roman, because that's exactly where microlensing is the most sensitive, and try to make that connection to atmospheric composition studies that we're currently doing with JWST. These far out distances are also the preferred formation locations for things like the super puffs. Currently, the super puffs are quite close in, which means they have to undergo migration, and slow enough migration allows for the multiple planets within a system to lock into resonance. That slow migration also allows for a high level of water enrichment, and that can lead to low C/O ratio as long as you can maintain that pollution at the upper layer where we can probe. And we see an evidence of this, or hint of an evidence of this for one of these super puff planets. And finally, when we try to think about the effect of sort of outer planet on the inner planets, we often consider the outer planets sort of act as a barrier, but it usually do not, both during formation and after. They do not generally act as like a barrier or blocking of the solid and volatile delivery. So I think a bit more care needs to be made when it might be not so clean when we try to make sort of dichotomy between what can we observe for the properties of the inner planets based on whether those systems have the outer planets or not. Thank you.